Try to mentally pack 3 different objects into a clean, empty digital room. On the surface, it looks like a simple game of organization. The earliest computers used a system called Contiguous Memory Allocation. The rule was rigid. Every time a new process enters memory, it receives one single, unbroken block. The system stacks them side by side. But computing is constant motion. When that middle process finishes and exits, it leaves behind an isolated, empty gap. This strict requirement for continuous space makes the system surprisingly fragile. Even basic computing tasks begin to create a layout that the computer can no longer navigate efficiently. As dozens of programs of all different sizes cycle in and out, the physical layout of the memory begins to break down. Over time, the grid becomes pockmarked with scattered gaps. This is fragmentation. If combined, you'd have plenty of room. But because the space is scattered, a new process cannot find a single block large enough to fit. This waste shows up in 2 ways. First, there's internal fragmentation. This happens when a process is given a block that's slightly too big, leaving a small pocket of unusable space trapped inside the allocated area. Then there's external fragmentation, where the free space is sitting outside the blocks, but it's too small and spread out to be of any use. This shattered geography eventually hits a wall. If the computer cannot find a way to fit data into these gaps, it simply stops being able to run new programs. If you were looking at a shelf with books spread out and gaps in between, the most obvious solution is to just reach in and push everything together. Engineers tried this exact approach with a technique called compaction. During compaction, the system moves the active processes so they sit flush against each other. This effectively sweeps all those tiny, isolated gaps into one large, usable block at the end of the memory. It solves the geometric puzzle. Like treating digital data like physical objects comes with a massive hidden cost. The problem is that moving massive amounts of data across physical memory requires an enormous amount of work from the CPU. This creates heavy system overhead. While the computer is busy sliding blocks around to organize itself, it has to stop doing almost everything else. You feel this at the keyboard as a sudden freeze. The system shudders and stops responding because the processor is too busy cleaning its own room to listen to your commands. Because of this heavy tax on performance, compaction turned out to be a dead end for any computer meant to handle more than one task at a time. To move forward, engineers had to abandon the very first rule we discussed, the idea that a program needs to stay in one unbroken piece. This led to the development of paging. With paging, the system chops a large process into smaller, uniform pieces. Because they are the same size, they don't have to stay together. This bypasses external fragmentation. These pieces drop into whatever gaps are available. There's no need to move existing blocks. By switching from physical movement to this kind of smart mapping, the system eliminates the massive performance drops caused by compaction. This shift in how we handle space is why modern devices don't crash the moment their memory starts to get crowded. When you have dozens of browser tabs open while streaming video and running a game, your computer is managing a chaotic puzzle behind the scenes, using paging to fit data into whatever corners of the memory are available. By treating memory as a flexible map rather than a physical shelf, computers finally gained the ability to scale alongside the complexity of modern software.